Erica Morgan. I'm a graduate student in astronomy at Vanderbilt University. I was born here in Nashville, Tennessee. Went to one of the academic magnet high schools here where I was first introduced to math and science. My father kind of put me in summer programs the entire time for engineering and science, so it was natural that I majored in physics at Tennessee State University for undergraduate. Around senior year of undergrad, I was introduced to the Fisk Vanderbilt Master's to PhD Bridge program. I thought it was ideal because I wasn't really certain whether or not I wanted to pursue physics in terms of graduate study, but it turned out that I did while working at Fisk. The Bridge kind of is designed for you to take core courses at Fisk to get a master's in Fisk. At the same time, you can cross-register at Vanderbilt University and take courses there as well. After you've completed your master's at Fisk, you end up getting core requirements for a master's while completing core requirements for a PhD at Vanderbilt University. That way, you can make that transition.
And so this is the last that I want to say about this, but I wanted you to see that there are multiple lines of evidence, actually, that lead us to the same basic conclusion.
I use coupled models to recreate the environment between the Earth and the Sun. The goal is to improve prediction of the Sun's activity and how it affects us here on Earth. The Sun is extremely, extremely active. Hot gas kind of comes off of it pretty much on a regular basis, but sometimes much larger amounts come out at much powerful speeds, causing high amounts of radiation. And that hits our Earth's atmosphere every once in a while and causes problems with our satellites and communication. Everyone's concerned about being able to know where everyone else is on the globe, and sometimes that becomes a concern when the Sun becomes more active. It has been studied already that the Sun goes through a certain rotation period where it's more active and shoots out more hot gas than other times. We call them solar flares and coronal mass ejections. They happen more often, and sometimes they're directed towards the Earth. As far as solar flares, they produce large amounts of ionized particles. Because of that, it saturates our atmosphere, which is made up of ionized particles. So we depend on that delicate balance in our atmosphere for communication. And when it gets super saturated, it moves our satellites out of orbit. Eventually, I want to get into science policy, and I will probably end my career up in the classroom. I really want, at that point, to share my experiences and what I know with students.
I am Felipe Colazo. I am a graduate student in physics at Fisk University, and I am also part of the Fisk Vanderbilt Bridge program. I've always had an interest for astronomy. So as soon as I came into Fisk, my advisor at Fisk, Dr. Arnold Berger, mentioned a few programs that they had between Fisk and Vanderbilt, and one of them was taking classes here in astronomy. I'm interested in instrumentation, so it has to be something with my hands. I'm really, I want to think I'm really good building and in assembling things. But I also want it to be that if I build something, I want it to work perfectly and you can use it for some scientific purpose. So right now, LabVIEW is telling us that it has something unwired or placed in the block diagram that is not connected to anything. So we click on that, and when we click on the one that doesn't like, it's telling us wired it or something's wrong with it, we click on it and we go directly to the front panel and we see what it's talking about. So in my undergraduate background, I did a lot of interns. I did 3 internships building things. You know, one was with soft X-rays, testing X-ray filters. The past summer, I actually started a program at Goddard Space Flight Center at NASA in Maryland. And there I built a very low energy detector for what they call zodiacal light. Well, zodiacal light, in a sense, is dust particles in our solar system, okay? From the sun out to, let's say, Jupiter or so. Then these dust particles are steady within the solar system. So there's this scientific theory that says that every particle needs to, or is going to rotate and eventually die in the sun. So if you think of dust particles, the gravity pull from the sun would be really high, and so there wouldn't be any dust. But when you look out from Earth, you see a lot of these diffused particles. So these particles diffuse the light coming from the sun and other stars, of course. So we want to study these gas clouds, okay, and understand their dynamics, the way they move. Why are they being recreated if we know that they should be dying in the sun? And if they are being created, where are they coming from? You have to tweak your instrument, you have to modify little things, you know, up to you get to a perfect stage where you know that you are actually getting the data that you want. Then after that, you get some data and then you start processing it, you know? So it's not only, you know, getting your hands dirty and putting a detector together, but also, you know, analyzing what this detector that you have put together has obtained for you, and then processing that and getting actual results, beginning to end, is just, to me, is just fantastic.